Okay, so I asked you guys to create the structure of water. Water is going to look like this. This is called a bent shape. Water technically on the oxygens has two lone pairs. But when we name the shape, we just look at the bonded atom shape. According to our Lewis structure, water would look like a line with two lone pairs, but we see it's a bent shape. So how does that work? I also asked you guys to create the shape for carbon tetrahydride, or common name is methane. What we see here is on the Lewis structure, we would have thought it looked like a cross, but instead it's what we call a tetrahedral. By the way, look at how similar water looks to carbon tetrahydride when we include the lone pairs. Then, of course, we have CO2, which on the Lewis structure looks like a line. We kind of have a line shape, except the double bond is kind of chunky monkey. Okay, it's a little fat compared to the single bond. Guys, stop talking. Okay, and so the question is, how did we get from these to these 3D shapes via the 2D Lewis structures? So we're going to flip over to our notes now and talk about molecular geometry. And I realize I need to screen share. That would be very, very helpful. We're going to do that right now. Okay, let the games begin. Whoop, whoop. So, molecular geometry is the 3D illustration of molecules and how atoms bond or connect, right? So we use some molecular modeling kits to warm us up. And what we see is that the molecular geometry is based off your Lewis structures. So there's a really important theory known as valence shell electron pair repulsion theory. I call it VSEPR theory, that tells us why we get the weird shapes that we do. Why isn't carbon tetrahydride a cross? Why is it this tetrahedral claw looking shape? Well, it's because of this. Since all electrons carry a negative charge and electrons are what are being shared in bonds, okay, the electron pairs, the electrons being shared, will arrange themselves in a way that maximizes distance and minimizes, how do I spell minimize? Minimizes repulsion between the electrons. So you kind of got to think about it this way. When you don't like someone, but you have a common friend and you're asked to hang out with them, you stick your friend in the middle because you want to maximize closeness. Sorry, you want to maximize distance between the person you don't like, but minimize the repulsive interactions you could have with them, but stay near the center atom that you actually like, the friend that is a mutual friend. So you sit literally in a line. If it's 3 of you, you would put your friend in the middle that you both like, and the people that you don't like, that you're repulsed by, you would maximize the distance and be a 180 from them. Same idea with electrons, and particularly how atoms arrange themselves around the central, how terminal atoms arrange themselves around the central atom. We also call these, by the way, repelling forces, and or electron domains. It's 2 ways of saying the same thing. So if you look at this image to your right, you see a central atom A bonded to 3 terminal atom Bs. They will arrange themselves in such a way that the 4 repelling forces, repelling force number 1, repelling force number 2, repelling force number 3, and the lone pairs on the central are also a repelling force. This has 4 what we call electron domains, or 4 repelling forces that will arrange themselves around A to be the furthest apart from each other, but still connected to A. Okay? And this is useful because what it does is this theory allows us to explain and predict the 3D shape and resulting bond angles. Because there's an angle that comes with this 3D shape. What is the angle between these two? What is the angle formed between this bond? What's the angle formed between this bond? Right? The bond angles around the central. So what is equal to one repelling force or one electron domain? What is actually equal to that? Well, what we say is it is any source of electrons around central atom. Notice how I keep on saying central, 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 central. Okay? It's the shape around the central. So what we say is we would add up any single bond, any multiple bond, so double or triple, a multiple bond, right? We call those multiple bonds. Okay, and 3, any lone pair around the central. I don't actually care about the lone pairs around the terminal atoms. I care about the shape created by the central. Notice, I didn't mark any of these lone pairs as being a factor to consider. I only marked the lone pairs around A, the central. Yes.
What if it's only just one?
Radical, you will not be given a problem like that, so not to be concerned. Okay, so we actually can develop a pattern out of this. When we look at specific combinations of electron domains around a central, we get a pattern where we can align it with a specific bond angle. So 2 electron domains, such as carbon dioxide, will have a bond angle between the 2 atoms or between 2 of the terminals of 180 degrees. 3 electron domains, such as boron trihydride, would have a bond angle of 120 degrees between each electron domain. Each single bond did hydrogen. And then, this is where it gets a little weird, 4 electron domains will have a bond angle of 109.5 degrees. And we do know it's 0.5. That would be like carbon tetrahydride. No, you're like, what? That doesn't add up to 360. Remember, it's 3D space, man. You can get the x-axis involved, right? That's why you get the claw. Math. Okay. There's more, and there's a whole table, which, by the way, you will be memorizing.
Oh.
Okay, so far we have covered 2, 3, and 4, where there's 2, 3, and 4 electron domains. But we can have a 5 electron domain where we have 5 things attached to it. Okay, 5 sources of electrons attached to a central. We call that, okay, trigonal bipyramidal, and that is a combination of 120 degrees and 109.5 degrees. By 120, I totally meant 90, sorry. 90 degrees and 109.5 degrees. There's a 90-degree angle and sometimes a 109.5 degree angle between the two. Okay. And for octahedral, when you have 6 electron domains, it's all 90 degrees with 180, right? From top to bottom. Yeah. So, and I made a mistake. It's 190 and 120. Sorry, guys, I'm going off of memory too. It's 90 and 120 bond angles for 5 electron domain. And it's 90 degrees all around for octahedral, 6 electron domains. And I know the terminology is a pain in the arse, but you do have to learn it. So let's learn how to read the rest of the table, because it's kind of easy to memorize 6 things with their names. That's decently easy. Okay. What's all of this stuff over here? Like, what's all that? We're going to talk about it. So let's look at water. We know the Lewis structure for water is going to be this. The question is how many electron domains? And by the way, notice you always have to start with the Lewis structure before you can predict the molecular geometry. So water has 4 electron domains. And I'm going to name it ED. How did I get those 4 electron domains? 2 single bonds, 2 hydrogen, 2 lone pairs around the central oxygen, giving me 4 electron domains. Originally, we would call that shape if we included the lone pairs. We call that electron geometry if we include the lone pairs. If we include the lone pairs, we would call this a 4 electron domain tetrahedral. But when we name the molecule molecular geometry, we only name based off of the bonded, connected domains. So we say there are how many lone pairs around the central atom? 2 lone pairs around the central atom, giving me for water, bent is the actual shape of water, which is what we saw. It is bent. 2 lone pairs around the central, but the name of the shape is bent. If we include the lone pairs, it looks tetrahedral, but we don't when we name it the molecule shape. If I was asking for the electron geometry, then you'd include everything. But I'm asking for just the molecule, the bonded part. So you see when I read the table, I say, I start with my original amount. And I say, do I have any lone pairs? Yes, I do. How many of them? 1, 2, all the way over bent. Does that make sense? How to read the table? It's kind of like bingo. Kind of like the periodic table, right? Yes. It has 4 electron domains originally, but no, it has, but remember, lone pairs around the center also count as 4 as an electron domain. So anything around the center is an electron domain. So what I have to do is I start with how many total sources are attached to the central. Then I figure out if any of those, Liam, if any of those are lone pairs, I have to move over to the right on my table to predict the actual shape based off of the bonded portions. But the lone pairs still affect the shape. We just name the shape off of the bonded part. So it was tetrahedral, but it's technically bent because 2 of these are lone pairs. So I'm going to name the shape off of these 2. Because it has 4 electron domains. An electron domain is a single bond, double or triple, or a lone pair. Mm-hmm. Yes, excellent. So anytime you have a lone pair on the central, your molecular geometry will look different than your electron geometry, what you would think it would be. Okay, next one, CO2. That's easy. Okay. Oxygen, carbon, double bonded. We have what we say is 2 electron domains from the 2 double bonds. Now, here's a common mistake that happens. You see 2 double bonds, you say, oh, 4 electron domains, 4 lines. Not here. Here it's general source. We're going to count 1 double bond as 1 source of electrons off the center. So we say 2 double bonds give me 2 electron domains. I have no lone pairs. So according to my electron geometry, I am linear. And since I have no lone pairs, I am also molecular geometry. I am linear. They match. No lone pairs. Okay. So tomorrow, we're going to warm up with question 3 and 4, where you guys are going to draw the Lewis structures and tell me the molecular geometry by assigning electron domain. But in the last couple minutes of class, I want to hand out your practice test for you to start working on in preparation for your test on Friday. Okay, so there's a digital version on Canvas and on my website. And there's physical copies up here if you would like to grab a practice test to start working on tonight for homework. Okay. All right, guys, really good job today.